Nirajan, I am not able to hear you.
Okay, ma'am, I have started the recording.
Yes. Okay. Yes, it is started. So let me share the screen, then we will uh, start the content show after that. So I hope the screen is visible to you.
Yes, ma'am.
Yes. Okay. Uh, Today we will start the new topic as far as this design course is concerned, and that topic is the uh, pressure vessel designing under external pressure. So far we have seen the design of pressure vessel based on internal pressure, and for that we have already covered the design of shell, design of heads, design of flanges, okay, and tall vessel design along with the support. However, support for usual vessels which are not falling in the category of tall vessel, support for that is remaining, so that we will cover in subsequent classes. So today we will cover this vessel under external pressure, and last class we have completed the design of tall vessel along with the along with its support, and that is a specific support which we call as the skirt support, or the um, that support which is uniform from all side. Okay, and we have discussed the design of that. In that design we have covered the thickness of sheet, thickness of support, and along with the bearing plate thickness, and whether anchor bolts are required or not, and along with the number of bolts that will be required, right? So in that so that was about the tall vessel, and I think considering internal pressure design, almost all part we have covered except the support. So that is the case, and now we will consider the vessel under external pressure. And I believe that by now you understand the meaning of internal pressure and external pressure. External pressure means, or internal pressure means, wherever I am facing the higher value or higher magnitude of the pressure. Okay, if internal pressure is more than outside pressure, we consider that as internal pressure design, internal pressure vessel. And if external pressure is more than internal, we call that as external pressure vessel. So its design is entirely different, because the stresses which are applicable over here, that will act in different direction. Okay, uh, so what these stresses are and where these are acting, what type of failure occurs, so that we need to focus more on the design part, and all these points we will cover in today's class. So as far as you understand that when we consider the chemical process equipment, okay, chemical process equipment, many process equipment are operated under the external pressure, where uh, either uh, we consider that internal pressure is lesser than outer pressure. Okay, maybe this is the case, or if internal pressure is atmospheric, external pressure is more than the this atmospheric pressure. So all these conditions fall under the category of external pressure vessel design. Okay, so when we consider the external pressure, why it is so? Because of the reason there, when we are operating at vacuum. Okay, so if inside the vessel vacuum pressure is there, and outside the pressure we have atmospheric pressure, so of course outside pressure is more than the inside pressure, so it will fall in the category of external pressure. However, the operating pressure or the design pressure, whatever we are considering, that is of the column only. Okay, just wait please, huh? अच्छा, एक second, just I am starting. Okay, please wait. So I'm sorry for the interruption. Okay. So one point is when I'm having the internal pressure, when I'm having the internal pressure, it means inside the vacuum and outside the external pressure. And second condition is when inside is atmospheric pressure and outside is higher pressure. Okay, or we can have the combination of both. Okay, so just wait, please wait. I will start. I'm so sorry for the interruption again and again. Just 1 minute, please. So sorry for the interruption. Uh, so we basically have two different condition. One is inside vacuum, and second is when inside atmosphere and outside is uh, more than atmospheric pressure. Okay, or we can have combination of both, means inside vacuum and outside more than atmospheric pressure. Okay, and when we consider that whether this type of situation occur in chemical industry or not, the of course it is occurring, and very common example for that is multiple effect evaporator. Okay, so you all must be aware about the operation of this multiple effect evaporator, that the whole system of this evaporator is it is being operated under vacuum. Okay, when we have either one effect, two effect, three effect, whatever would be the number of effect, at the last or we can say near the last effect, we have the vacuum pump which creates vacuum in all effects. Okay, and because of this vacuum the feed travels on its own. Okay, when it is of course in what we can say forward direction, in backwards direction because we have a pressure difference. So for that we used to we usually use pumps, okay, to move the feed in backward direction or backward sequence. Okay, so in that case, when we consider the multiple effect evaporator, these are basically fall under the category of external pressure vessel. Okay. Similarly, we have distillation column which can be operated under vacuum. So that is designed considering this external pressure vessel design steps which we are going to discuss. Okay, here. So Uh, when we consider this external pressure vessel design, what are the stresses which are acting? Okay, and in that case, we usually have cylindrical vessels, not the spherical vessels. Okay, so cylindrical vessels that you understand that we have the cylindrical shell. Okay, and head will be closed either from either with the flat type or we may have the dome type or form type. Okay, formed is the right word. So, because of this external pressure effects, the cylindrical vessel experience an induced circumferential compressive stress, which is significantly of higher than the longitudinal compressive stress. Actually, when you visualize this external pressure vessel, you can understand like inside the vessel we have lesser pressure than the outside. So obviously from anywhere the pressure will be towards inside, towards inward, which we consider as compressive stress. Okay, just reverse to internal pressure vessel, like when internal pressure is more, it will try to what we can say to put outward. Okay, or we can say in tensile way, tensile stress. But here from everywhere the pressure tries squeeze the vessel, and therefore it is compressive stress. And when we consider the cylindrical vessel where length is significantly higher than the diameter, longitudinal compressive stress which will work from two sides across the cross section, right, across the cross section from two sides. Okay, so you can understand that diameter will be cross section, what we can say, the diameter is diameter will play its role. Okay, so that will be because that acting area will be quite less. However, when I am considering circumferential compressive stress along the length, it will try to squeeze it. Okay, therefore in this case circumferential compressive stress is usually twice than the longitudinal compressive stress. Okay, therefore we need to we need to keep these vessels safe along the length. Okay, if we can keep the that safe safe along the length, obviously along the what we can say cross section, that is already less. Okay, so it will, so failure mostly will occur from the circumferential side. Okay, and the reason I have already told you, because compressive stress circumferential side is twice in comparison to longitudinal compressive stress. Okay, so when we consider external pressure vessel design, uh, we basically start with at what condition failure may occur, so that we can design to save that failure, and then operation will remain operation will be safer in safer under operating condition. I hope you are getting my point. Um, the same thing we have discussed in internal pressure, because we have considered all parameters uh, that is close to the failure, like allowable stress, okay, that is less, just lesser than the damaging stress, okay. So we basically imagine the extreme condition, and then we consider the design of that, considering that situation, so that we can always remain in safer side. So when we consider when we consider external pressure vessels, these are subjected to two kind of failure. First is elastic instability, which we also called as buckling. Okay, elastic instability, and it occurs when we have stress which is lesser than the proportional limit. Okay, so elastic instability means when the pressure vessel face this type of situation, we can have uh, when further we would like to maintain that the actual shape can be maintained. That is the condition for elastic failure or elastic instability. Okay, and this is specifically we categorize as buckling, and which is usually occur when let's say we have lobe in the shell. Lobe means, let's say if I am having the dent, okay, so in that these dents and all, these are more close to the failure. Okay, so if this type of irregularity occur in the shape, we usually face this elastic instability, and that happens when we have the stress which is lesser than the proportional limit. Secondly, we have the plastic instability that we call as permanent failure. Elastic instability, temporary failure, when we push the what we can say, the pressure and all, it takes its own shape. Okay, but plastic instability, that is permanent, and that happens when the stress is more than the yield point. Okay, when the stress is more than the proportional limit but lesser than the yield point. Okay, so this is the condition. And when we consider the proportional limit, it is defined as the greatest stress which a material can sustain without deviating from law of stress and strain proportionality, and that we all know very well as the Hooke's law. Okay, so elastic instability occur till we have the Hooke's law. Otherwise, we will have this permanent failure, and that is the plastic instability. Okay, so here you can understand this stress and strain graph uh, for any material. Similar type of graph you can say. Of course, some variation we observe in values, but the pattern will remain like this. Okay, so elastic failure will occur when we have this below proportionality limit. Okay, and that is basically the buckling, and that I have already told you, because of dent and all this type of instability occurs. Okay, so uh, and that also you have observed that in our cars and all, whenever we have the dent and all, that can be fixed. Okay, however, permanent damage is there, it means material breaks. Okay, so that cannot be repaired by this by pushing the pressure and some similar procedures. Okay, so this is the linear and elastic, so proportionality limit will be up to here, so elastic failure will occur in this region. And we have permanent failure when we considered this when we considered more than the this proportionality limit. Okay, so in that case you can have this failure. So the basic point to keep in mind is whenever we will design this kind of pressure vessel, we consider the elastic condition, we consider the plastic condition both, because once the plastic condition will occur, the repair is not possible. Okay, so we will see whether the our design, and when I'm speaking about the design, you should keep in mind I'm speaking about the thickness. Okay, so when the thickness of the let's say shell, that thickness is strong enough to sustain the plastic instability. Okay, so that we need to ensure. Okay, so this is the case. Now, as far as this external pressure failure will occur, uh, we already have seen before how the internal pressure failure will occur. Internal pressure failure can be understood as a vessel failing after stresses in part or a large portion exceeds the material strength. Okay, so this is the case that the internal pressure, whatever stress is being created in the specific part, if that exceeds the material strength, then the external pressure will failure will occur. Okay, so how it will look like? Okay, it will look like bursting. Okay, because internal pressure is more, it will try to rupture that metal sheet and try to release the pressure. Okay, so bursting will occur in that case. Okay, however, that you can imagine. Okay, this is the internal pressure failure, bursting will occur, and we have this rupture in the metal sheet, right? So this is the internal pressure vessel. However, when we consider the external pressure vessel, because internal pressure in that case is lesser. Okay, so external pressure is more, so it will try to squeeze the shape. Okay, so during external pressure failure, the vessel can no longer support its shape and suddenly takes a new lower volume shape, as you can see over here. Okay, so this is basically the internal, the sorry, external pressure failure. And you can see when this kind of thing is there, we can have the, because of course damage will be there, so fluid will come out from it. Okay, so this is the case. External pressure failure will squeeze it. Okay, and you can imagine this vessel. Okay, just if you see this these type of images, it looks like as if you are squeezing the paper. Okay, it is that kind of irregularity occur in the shape. Okay, similarly you can see this type of squeezing. Okay, and if you imagine what is this. Okay, if you see, this is nothing but the rail bogie. Okay, train where we have this cylindrical shape, like when the let's say some flammable fluids or petroleum products, all these are transported. Okay, so we have this kind of rail bogie with the cylindrical shape and formed heads. Okay, and you can see the type of failure. Okay, type of failure, and you all must have seen this rail bogie, and it looks so strong. Okay, it looks so strong in the shape, but when external pressure failure will occur, it is squeezed like a paper, as you can see over here. Okay, and it happens only in few seconds. Therefore, when we consider external pressure, we have to be very careful about the design, because failure will not take time to occur. Okay, in seconds it will squeeze. Okay, I will show you right now. I don't have any related video and all, but if you see in YouTube the external pressure failure, if you see, you can see the you can visualize the type of failure. Okay, so in few seconds only, okay, in few seconds only we have this type of squeezing in the shape, which will damage it completely. Okay, if it is not in the elastic range. Okay, so the point is how we can mitigate that, how we can uh, uh, mitigate that, even if you consider safe side for design. But of course you need to take additional measures to save, or to keep these vessels from failure. Okay, so in that case, whenever the pressure um, what we can say reduces inside, some type of spray is there, which keeps the internal pressure for in the what we can say in the same category. Because when we have this type of failure, right, when we have this type of failure, external pressure will remain as it is. When I'm having inside vacuum and outside atmospheric pressure, outside will remain atmosphere all the time. But when inside pressure is lesser than the vacuum we are expecting or we are designing with, if pressure reduces, then it will squeeze. Okay, so whenever pressure becomes lesser, at the same time some spraying is done automatically, so that the pressure inside the body will be maintained, right? Because this type of failure is very difficult to repair. Okay, and it happens in only few seconds, so that you cannot take any action except the that automatic. If it is, if it senses the pressure is reducing, then the vacuum, desired vacuum, the spray will on. Okay, so that type of measure we can take to to not have the failure in these kind of vessels. So this is the external pressure vessel. And now, as far as this design is concerned, because of the external pressure effects, the cylindrical vessel experience an induced circumferential compressive stress. And as I have told you that circumferential compressive stress is twice than the circumferential longitudinal stress. Sorry, then the longitudinal compressive stress. Okay. So, as a result, the vessel is apt to fail because of the elastic instability caused by circumferential compressive stress. Okay, so because this stress is more, so first failure will come from this only. So we need to consider the elastic instability, because first we need to save the elastic. Permanent plus or plastic instability will come later on. So if somehow we will able to save the pressure for failure under the elastic instability, we will it will be safe in plastic instability as well. Okay, so in that case, what measure we consider? Uh, the rigidity of the vessel. Okay, rigidity of the vessel under such condition may be increased by using uniformly spaced internal or external circumferential stiffening rings. Okay, we usually place stiffening rings to either internal periphery or external periphery. Okay, after regular interval. Okay, so that these stiffening ring will reduce the acting area of of this circumferential compressive stress. Okay. So this reduces the effective length of the vessel to center distance of the stiffeners. Okay. So the point is, when we consider the long shell, okay, from everywhere that circumferential stress is acting, it will try to squeeze it towards inward. Okay. However, when I'm considering stiffening rings, okay, what these stiffening rings and all these I will show you. So when I'm considering this stiffening rings, it means let's say my total length is 10 meter. Fine, total length of the vessel is 10 meter. So this circumferential compressive stress is acting along this 10-meter length. However, when I am considering stiffening ring after regular interval, so let's say after 1 meter I am putting a stiffening ring, 1 meter interval. Okay, so now the area which remain without any support is only 1 meter. Okay, before it was 10 meter. Okay, so this stiffening ring provide the rigidity in the vessel so that the failure will not occur, and that happens because the effective length of the vessel reduces, and that remain the distance between two consecutive stiffeners, not the tangent to tangent height. Okay, I hope you are getting my point. So what these stiffening rings and all that I will discuss. So here we have length to diameter ratio is therefore a significant parameter in determining the safe pressure under external compressive stress. Okay, so if you see L by D, L by D means length of the shell, and this diameter, outer diameter of the shell. Okay, so if length is 10 meter, this diameter is 1 meter, so L by D is ratio is 10. Okay, however, when I'm using the, sorry, when I'm using the stiffening rings after a 1 meter interval, L will be 1 in that case, not the 10. Okay, so L by D will be 1 by 1, so that would be 1. Okay, so in that case, this L by D is a significant parameter in determining the safe pressure under external compressive stress. Okay, if you see the stiffening rings, these are nothing but these kind of uh, the assembly placed or welded over the external circumference, okay, or outside the circumference. Okay, if you see here, this is the long reactor, long vessel, and after certain interval we have these kind of rings, okay, that you can see these kind of rings. Fine, more clearly you can visualize these rings over here. Okay, this is the ring, this is the ring, this is the ring, like this. Similarly you can have these stiffening rings. Fine, and when we consider this stiffening ring, effective length will be only from this to this. Okay, if these stiffening rings are not placed, the whole length is available to me for compressive stress to work on. However, when I'm having these stiffening ring, the what we can say, the length where that stress will uh, act, that will be this much. Okay, so this much, and then this much, and then this much, it is divided basically. Okay, it's not like that area we have cut down or something. No, area will remain as it is. Only the we can say this stiffening ring provide rigidity after putting this at regular interval. Okay, and if you imagine the type of stiffening ring, this is the stiffening ring. Okay, and this inner side, inside, from this side, not inside but this side is welded over the periphery. Okay, just please wait for 1 minute. I will start shortly. sorry. So in this way, you can imagine this is the stiffening ring, and this portion is welded over the external periphery. Okay, and if we need to place that internally, then this surface will be placed to inside the vessel. But mostly it is placed outside because it is not disturbing the process inside the vessel, right? So this is the stiffening ring. And when we place this stiffening ring, this is the distance. Okay, and how this distance is decided, that it will depend on the critical length. Okay, we always need to place the stiffening ring below the critical length. Okay, if it is beyond the critical length, then more length will be available for that pressure to act, and squeezing, it may squeeze this. Okay, so this is again very important parameter to consider in designing, that what should be the distance between two consecutive stiffening ring, so that can be decided by the critical length between the stiffeners. Okay, so the if stiffeners are placed within the critical length, they offer re- they offer restraint to collapsing of the vessel under external pressure. Okay, under such conditions, the vessel with same thickness can sustain higher external pressure. Okay, so we need to keep in mind that critical length we calculate, and distance between two consecutive stiffener will always be lesser than the critical length. So critical length we denote that as LC, is the distance after which elastic instability may occur. Okay, so here I am having this expression LC 1 point, which is equal to 1.11 d naught root over d naught by t. Okay, so d naught is the outer diameter of the shell, and t is the thickness of the shell. Okay, and this t we get from the design, so that we will see how to find this t value, right? So this is for the critical length between stiffeners. And another parameter for design of this shell under external pressure is out of roundness. Okay, out of roundness means if we have some irregularity in the shape. Okay, if it is what we can say, the shape is uh, what the shape is regular, we consider that as round shape. Okay, so this out of roundness is the parameter, and how we need to consider that. Before that, let's define this. So out of roundness in any form, okay, out of roundness in any form is very much detrimental to vessel strength under external pressure. It means this is out of roundness, when we consider, it causes failure to occur easily. Okay, as a result, the shell of elliptical shape or a circular shell with dent, okay, is less strong under external pressure than the vessel having a true cylindrical shape. Okay, therefore for external pressure, spherical type of vessel is usually not considered. Okay, either we have elliptical shape means that cylindrical, but the head will be of like ovoid form type. Okay, or complete vessel is uh, like elliptical in shape. Okay, so when I'm considering the regular cylindrical shape, okay, because it has the proper shape. Okay, and without any denting and all, so that shape is quite regular. However, when we consider elliptical shape, the uh, its shape is quite what we can say, its shape is not same from all side. In cylindrical shape, the shape is same from all the side when I'm focusing on the circumferential. Okay, but in elliptical shape, circumference will keep on decreasing, right? So if shell is having elliptical shape, or let's say if I'm having a cylindrical shape with dent, okay, where any type of irregularity in circumference is observed, that we count as out of roundness. If it is true circumference, if it is true cylindrical shape, we consider that roundness is proper. Okay, uh, and if it is not rounded proper, it is out of roundness. So out of roundness may be considered when I'm having not uniform circumference. Okay, when circumference will keep on changing, so that may be either elliptical shape or that cylindrical shape with dent. All these we need to consider. So out of roundness is very important parameter in design. Okay, so the first is we have this oval shape, or let's say this elliptical shape. For that we define this out of roundness as capital U, which is equal to 2 into this d max minus d minimum divided by d max into 100. So d max is the that major axis, and d minimum is the minor axis for oval shape. Okay, and that is the diameter for major axis and minor axis, 2 in 2, and that will be, because this out of roundness is basically we consider, so it will always be multiplied with n with 100, right? So this is for oval shape. For dent we have this capital U, which is equal to 4a by d naught into 100. A is basically depth of the dent. So let's say if I'm having 4 5 dent, whatever the maximum dent among these, that will be counted as the uh, for that we consider A, okay, which has the maximum depth. Okay, so in that case we define the out of roundness parameter. And this out of roundness, when we consider for old vessel, large value from above expression is to be selected. So if vessel is already existing, okay, and we need to find out of roundness of that, we will calculate out of roundness for this oval shape and for this dent, in both way, and whatever u is more, that we consider for design. Okay, however you can understand that if vessel is already existing, what is the point to consider that? Okay, so that you can find, let's say older vessels are there, and that all these out of roundness when we are calculating, based on that, when I'm having the suitable design, okay, suitable thickness of the shell, if that shell thickness is not maintained, is not there, we can provide some stiffeners and all to give the that to rigidity to the shape, right? So in that way we can consider this old vessel. However, for new vessels, where, because in new vessel no dent is there, if it is elliptical we can calculate that, but for cylindrical no dent is there, so we can consider u as minimum value, which is considered as 1.5%. This u should be considered because after regular operation that dent may occur, so we will consider that a priori. Okay, based on the experience, this u could be 1.5% minimum, right? So in this way we will consider out of roundness of the shell. And now we will consider the design part of this, in which we have to determine of the safe pressure. Okay, safe pressure to keep the vessel safe from elastic failure and plastic failure. Okay, so first of all I will consider the elastic failure. Okay, so in this case, the cylindrical shell under external pressure tends to deform inward as a result of external safe pressure. Okay, so whatever um, external pressure we are considering, it will work towards inside, or we can say it will work in a compressive way, okay, towards the center of the vessel. Okay, either it is from longitudinal side or circumferential side, and this as a result of external safe pressure. Okay, so safe external pressure P against elastic failure is found by this equation, where I'm having P, which is equal to KE T by D naught M. So E is the modulus of elasticity, T is the thickness of the vessel, corroded thickness of the vessel. So this T we need to find. DO is the outer diameter of the shell, and K and M are the constants. Now, if you focus on this particular expression, it shows that we have to find this safe pressure. Okay, so as far as design is concerned, we are already aware of the design pressure. Okay, design pressure for this external pressure we already know. Okay, and for that pressure, what should be this T? Okay, that we need to compute. So it's not about computation of the safe external pressure, but for the considering design pressure as safe external pressure, we have to find T of the shell. Okay, that is only the design part, right? Now, as far as this K and M are concerned, these are the constants, which is the function, which are the function of dO by L. So outer diameter and length you already know, and this K and M we can find using table 8.2 in BC Bhattacharya, and this is that table. Okay, here I am having this dO by L. Okay, K is there and M is there. So here I'm having different DOL and K and M value. You can read from here. If value are lying between two value, we can consider the interpolation. So that is the elastic failure, and then we need to consider plastic failure also, because if elastic failure is safe, we also have to ensure whether plastic failure is safe or not. Otherwise, the damage will be permanent. Okay, so for that safe external pressure, we considered here P, which is equal to 2F T by D naught. F is the allowable stress of the shell, T is the thickness of the shell, corroded thickness of the shell, by DO, outer diameter of the shell. And this is applicable when DO by L is more than 5. Okay, if DO by L is less than 5, we need to consider safe pressure by this expression. Okay, where U is the out of roundness, other parameters you are already aware. Okay, so uh, now what should be the design procedure for that? Okay, you should keep in mind always that elastic failure becomes what we can say, it happens earlier than the plastic failure, right? So what we will do over here, first of all, you are already aware of the design pressure that I am considering as the safe pressure. Okay, please try and understand that design pressure I am considering as safe pressure P. Okay, sorry. For that design pressure, I will calculate this T. Fine. And because it is corroded thickness, so you don't need to add corrosion allowance into this. You can directly take the value higher than this T from table B1. Fine. So that is the standard thickness, okay, available in the market. So whatever design pressure I am having, okay, outer diameter I already know, L I already know, so K and M we can find by the table which I have just shown you, and we can find this T, right? Now this T I will put over here in safe pressure expression. Okay, do by L, if it is more than 5 or less than 5 or equal to 5, that you can check, there is no issue. So we will put this T in these expression, suitable expression, and we will calculate this P. Okay, we will calculate this P. Okay, now if this P, okay, safe external pressure for this T, if it is more than the design pressure, please try and understand. T, first of all, we have calculated from elastic failure. That T we have put in the expression of plastic failure, and we will calculate this P. If this P is more than the design pressure, fine. If this P is more than the design pressure, it means whatever thickness we have calculated, that will keep the vessel safe from elastic failure as well as plastic failure. I hope you are getting my point, because when a design pressure whatever I am considering and safe pressure is coming more than the design pressure, and design pressure will not exceed than the design pressure during the operation. Okay, so plastic failure will never achieve, will never come. Fine. So this is the condition. However, if I calculate thickness from the this considering design pressure as safe pressure and put this thickness over here, if this P is lesser than the design pressure, fine, in that case what I will do, I will calculate the thickness considering plastic failure. Okay, so this P will be then the elastic, sorry, this P will be the design pressure, and whatever thickness I need to calculate, that I will calculate from this T. Okay, and we can understand that if I can save the plastic failure, elastic failure will be safe automatically, right? So this is the procedure that I will also explain through the example, so that it will be clear to you more. Now so this is basically about the design of external pressure. Fine. Now circumferential stiffeners, this is also the part of the design. Okay, like which type of stiffeners I should choose. Okay, so circumferential stiffeners are used in external pressure vessels to improve the rigidity against collapsing. Okay, for that purpose the stiffeners themselves should be rigid enough, then only it will keep the rigidity, right? So sorry, so these stiffeners should rigid in itself. Okay, so we can have this these stiffeners. We need to check these is the what we can say, the strength of these stiffeners with one value, and that is basically moment of inertia. Okay, so the value of moment of inertia is the measure for such rigidity, and this moment of inertia is basically, we can consider second moment of inertia, and that we also call as area moment of inertia. Okay, so I hope all these term you already aware of. Okay, so the basic point is the moment of inertia of a stiffening ring and the shell. Okay, the moment of inertia of a stiffening ring and the shell that act together to resist the collapse of the vessel under external pressure. Okay, so the point is uh, We will calculate moment of inertia for the complete structure. Structure means for stiffening ring and the shell. Okay, and that moment of inertia should be lesser than the moment of inertia of the stiffener. Please uh, listen it carefully. uh, Moment of inertia of the structure, that should be lesser than the moment of inertia of the stiffening ring. Then only we can choose that stiffening ring as suitable ring, right? So first of all, I need to find the moment of inertia of the stiffening ring uh, and the shell. So this is basically moment of inertia of the structure. Okay, so moment of inertia of the structure, all these parameters you know. T is the corroded shell thickness, do outer diameter of the shell, and capital L is the distance between stiffeners. Okay, distance between two consecutive stiffeners, and AS is the cross sectional area of one circumferential stiffener. So how this AS will be obtained, that we will see. Okay, and F is the allowable compressive stress um, of the shell, right? So in this case, I is the moment of inertia of the structure. So moment of inertia of the stiffener should be more than the moment of inertia of the structure. Okay, so that we need to keep in mind, and we need to choose the stiffeners based on this I value, right? So how all these will be chosen, and what are different stiffeners and all, that we will discuss. Okay, so any external metal welded or rigidly uh, held along the circumference, that can be considered as stiffener, provided it satisfies above condition. Okay, so the point is, we need to satisfy this condition. Moment of inertia for stiffener, I will we will calculate, and this should be more than the this I. Okay, then only we will choose that stiffeners. Okay, so any external metal welded or rigidly held along the circumference can be considered as stiffener, provided it satisfies above equation, right? In determining end side effective length, 1 by 3 depth inside of formed head is to be added to the cylindrical length. Actually, when I'm considering the cylindrical length, the edge of that cylinders have the heads. Okay, if head is what we can say, if head is flat head, it is fine. If it is formed head, it means you should understand that the circumference will keep on decreasing in these formed heads. Okay, I hope you are getting my point. Okay, uh, so that will be the case of out of roundness at the head. Okay, and because that head um, height is lesser than the cylindrical length, we will not consider that in out of roundness. However, we will consider that part of the formed head, we will add that length in the cylindrical length. Okay, let's say total height of the formed head is 1 meter. Okay, that is inside, it means hi. Okay, sorry. So that means hi. So hi of the head, I will show you what I am talking to, and this you can also see when we have discussed formed head. So hi, ho, sf, all these value you already we have already discussed. Okay, so this hi basically the height of the formed head inside, and 1/3 of that we will add in the cylindrical shape length. In the cylindrical length, let's say length cylindrical length is 10 meter. and this height, inside height of the formed head is 1. So the total length of the cylindrical section will be 10.33. One third of that length I need to add. Okay. For one side formed head, if both side formed head is there, it should be twice. Fine. So instead of 1 by 3, we will consider 2 by 3 of HI. Right? I hope you are getting this. Otherwise, it will be more clear when we will discuss one example. And we will have moment of inertia of various cross section as which are shown in appendix C of BC Bhattacharya book. Actually, that is very important book for the design, so I will bring that book with me. Okay, so then you can make the a copy of that, right? So moment of inertia of various cross sections are shown in appendix C. So if you see what these values are shown in appendix C, that I will let you know. Okay, but if you see the stiffening rings, it also has different shape. Here I am having I beam, here I am having channel. So if you see, this is the parameters of I beam. Here I am having H, height of this, and this B is the width of this I beam. Okay, now if you see, here I'm having XX and here I'm having YY. Okay, so what it signifies that when this I beam is welded at this part, I hope you are getting my point. Okay, because when we consider the stiffening rings, these are like this. Okay, so if you see, this is B. Fine, this is B. This height is H. Okay. Now, if you are welding this stiffening rings from this side, fine. It means this is assembling to this side. Fine. So it means you are computing, or sorry, it means you are welding this at X side. Okay, this is X. Okay, it means YY will remain upward. Okay, this YY will remain upward. So what it signifies, please try and understand. I'm just I'm trying my level best to make you understand that if I am welding from this side, it means this will remain upward. Okay, in that case, the inertia should be YY side. Okay, if so that I will consider as moment of inertia. Fine, if it is welded in this X side. Fine. If it is welded in Y side, let's say if this part and this part is welded over the periphery, in that case Ixx will be the required moment of inertia, which you need to check with the moment of inertia of the structure. Okay, I hope you are getting my point. So this is for like I beam. Similarly for channel, this is total height, width is B, and if it is welded from this side, okay, welded from this side, so I need to consider as required moment of inertia, and if it is welded from this side, okay, Ixx will be considered as moment of inertia, right? So now we will see how table how this appendix C looks like. So this is for I beam. Okay, these parameters are for I beam. These are the standard designations. These are the standard designation. Sectional area A is given for this. Okay, so whatever AS you are counting, you are considering, this is nothing but this value. AS, I hope you understand this value. Cross sectional area of one circumferential stiffening rings. Okay, so this is a standard for each type of or each size of uh, um, stiffening ring. This is specifically for I-beam. So this is sectional area, this is H, this is B. All these parameters are given. Now here I am having moment of inertia. Okay, so here I am having Ixx and Iyy. So accordingly, if it is placed vertically, you need to consider moment of inertia as Iyy. If it is placed horizontally, you need to consider Ixx as the moment of inertia of IB. Okay, I hope you are getting my point. And similarly, I'm having this channel as the stiffening ring channel. I have already shown you. These are some designation with the required size, and sectional area is shown over here with respect to each. And please don't consider any interpolation and all, because these are standard values. Okay, what if your you need if somehow you are getting lesser area, let's say you need to choose any specific channel. Okay, for that you will consider, you will calculate cross sectional area, and that cross sectional area, if falling in between any two value, you need to consider higher value. Okay, because interpolation you cannot do over here. These are the standards, right? I hope you are getting my point. So this is for channel. Sectional area is shown as A. H, I have already shown you in the schematic. B, that you already know through the schematic. And here I am having moment of inertia in Iyy, moment of inertia as Iyy and Ixx. Okay, so depending upon the position you can sorry, depending on the position you can place these channel. Okay, and calculate moment of inertia accordingly. Okay, now I hope some time left to me, so I will cover this example. Okay, if time will not be there, please let me know, otherwise I'm continuing. Okay, so here I'm having one example. Uh, it is like an absorption column. Okay, uh, is 5.2 meter in outside diameter. Okay, just give me 1 minute. I'll start, please. I hope I am having some time. Yes. Okay. Just in few minutes, few seconds, I will start. Uh, okay. Sorry. Okay, so here I'm having the example like uh, We have an absorption column with 5.2 meter outside dia and 10 meter length, okay, from tangent line to tangent line of the closure. So I believe you understand this tangent to tangent length, that is from head up to heads, okay, at which head is attached. Okay, so that is nothing but the length of the shell. The tower is to be designed for full vacuum, as P is given as 0.1 mega Newton per meter square. So this P is given. Okay, this is again in the gauge. If it is an absolute, you need to convert that into gauge. Okay, and this is at 400 degrees Celsius. Assume a standard dished heads is, sorry, assume a standard dished head at one end of the tube or of the tower, and flat head at other end of the tower. Okay, this is not the tube, this is tower, sorry. Okay, so dished head is placed at one end, flat head is placed at another end. Okay, specification for standard dished heads are Ri is equal to Do. Capital Ri, you understand, for dished head, this is crown radius, right? So you can refer the content which we have covered in design of heads. Okay, so for formed head or dished head, Ri is the crown radius, which is equal to Do, outer diameter of the shell. Okay, Ri, small ri is knuckle radius, which is equal to 2.05 Do. Do you already know, so you will be aware of this Ri, capital Ri and small ri. SF is the straight part in the head. Okay, that is 50 mm. So that I will show you, or we have already discussed in design of heads. Okay, so the material of construction of tower is carbon steel having allowable stress value of 100 mega newton per meter square. So allowable stress of the material is given, and modulus of the material is given as 2 into 10 power 5 mega newton per meter square. What we need to find, okay, first of all we have to find the required thickness of the shell without stiffeners. Okay, so without stiffener we will find the thickness of the shell. And second part is we will find the thickness of the shell with stiffeners, which are located at 1 meter spacing. Okay, 1 meter spacing interval we need to place a stiffener, so effective length will be 1 meter in this case. However, without stiffener the effective length would be 10 meter, right? And some part of the formed head, that all we will discuss. Okay, so part C is estimate the saving in shell material if a 18 centimeter channel is used as stiffener rings. Okay, 18 centimeter channel, this is the standard for the channel. And this channel we need to consider as the stiffener. Okay, some parameters I already know, such as weight of the channel 14.6 kg per meter, uh, and moment of inertia of the channel is 8.9 into 10 so minus 3 meter 4. Out of roundness is given as 1.5 meter. Density of the shell and stiffening material both are same, and that is 7850 kg per meter cube, right? So in this way we can find out the uh, in this way we are given some parameters, and these parameters will be used to estimate the saving in a shell material, right? So all these parts we will discuss. So let me start with the first part. Okay, and that is basically the this thickness, required thickness of the shell without stiffener. Okay, so the point is, uh, uh, you already know, okay, like when we are considering any external pressure design, the first thing is we need to calculate the thickness for elastic condition, and then we will what we can say, we will consider or we will check the plastic condition based on that. Okay, elastic condition, thickness we will put in plastic condition, and then we will see whether the thickness is suitable to withstand plastic condition pressure or not. Okay. For that we need to, if you recall the elastic uh, what instability expression, p was equal to k and d naught and t, and we have m also. Okay. All these parameters we should find. So we need to find k and m for the from the table, and this k and m will depend on do by l. Okay. And here we need to first find out l. So for that, because this is the cylindrical part, okay, cylindrical shell, one part of this or one closure over here is the flat head. Okay, another head is the formed head, as you can see over here. Okay, so in this case, total height of the shell is given as 10 meter, but some part of this we also need to add in this length to account the irregularity, or we can say the irregularity, or we can say form section in this head, right? So for this I need to add 1 by 3 of hi. Okay, what is this hi? hi is basically this. Okay, if you consider this is hi. Okay, up to here we have the length 10. Then sf we already know. Okay, straight part in the head, that we already know. And then I need to find this hi. Okay, so this hi we can find by this expression. This we already have seen in design of head, nothing new is there. Okay, so that you can see in design of heads. So hi is basically it is equal to capital Ri minus root over Ri minus di by 2 into Ri plus di by 2 minus 2 small ri. So capital Ri 5.2, because that is equal to do. We are already given that. And then the small ri is 0.05 into do. So accordingly I can find out capital Ri and small ri, right? Outer diameter we already know, that is 5.2 meter. Okay, and that this we can assume to be equal to di also. Okay, because do is given to us. Okay, sf 50 mm, that is known to me. Now hi I can find by this expression as 0.8493. So the total effective length would be l prime, which is equal to 10 plus 1 by 3 into this hi. Okay, plus zero 0.0 sf. Okay, actually in second side or another side we have only the flat plate. Otherwise, if formed head will be there, we need to add this sf twice, and this should be 2 by 3. Okay, so because one side is having only flat head, we need to consider form section only another side, only in one side. So it is used to calculate l effective. So l effective now is 10.33. Okay, now to find out that k and m, I have to consider do by l. So do by l prime, and it is coming as 0.503. Okay, so if you see there is no value from 0.503, so we will interpolate between zero point 0.4 and zero point 0.6. So these are the value of k and these are value of m. Okay, so you can see for this k value 0.4 minus 0.533, 0.533 minus 0.6, that is basically equal slope. Then only we can do the interpolation, right? So zero point 0.4 value is coming as 0.246 minus k divided by k minus 0.516, which is given at zero point 0.6. So considering this, I can find the k value is coming as 0.38506 and m value is coming as 2.4609. So considering this k and m, I can find the required thickness of shell without stiffener. Part 1. Elastic instability, when we are considering, the expression is this: P is equal to KET by D naught and M. K and M we already have calculated. DO I am aware of. E I know already. And this P, which is the safe pressure, which we also consider as the design pressure, and that is given as zero point 0.1 mega Newton per meter square in gauge. Okay, so it will always be in the gauge. Okay, so considering this P and all other value, we can find this T value, corroded thickness, and it is coming as 21.08 mm. Okay, and next value, then this you can see from table B1, and so we can find this standard thickness as 22 mm, right? So this is for the elastic failure. Now the procedure is, once I calculate the thickness in elastic failure, that I will put in plastic failure equation, and then we calculate the pressure, and that pressure should be more than the design pressure at which I have calculated this thickness, right? So if you see, thickness we have put over here, and that thickness is only the corroded thickness. Okay, because when I'm having the corroded thickness, pressure is in the safe line, of course the standard thickness will give me the safer design, more safer design. Okay, so I'm so sorry. Sorry. So so that plastic failure expression is this. Okay, here why we have considered this, because do by L is less than 5. Okay, do by L over here is 0.503, right? So we will use the expression where do by L is less than 5. So this is the expression. 2F, that allowable stress, it is given as 100. T, we are considering this 21.08. DO I already know, and here I am having this U. Okay, that is basically the out of roundness in percentage, which is given as 1.5%. Okay, and the other parameter you can consider. No, there is no issue. Mm. Okay, so if you see here, do by L prime is coming as 0.503, which we have considered as it is. Okay, so that with L effective length, right? So considering all these parameter, you can find this P, which is coming as 0.1353 mega Newton per meter square, which is more than zero point 0.1. Okay, mega Newton per meter square. It means the plastic failure will occur at more pressure than the design, and you understand that design pressure which is not exceeded in any condition. Okay, so of course some instrument failure will occur, then that is possible, but it is knowingly this pressure won't increase. So plastic failure will occur at more pressure. It means we will always be in the safe side. Therefore, the calculated thickness is safe against plastic deformation, and that is equal to which is equal to 22 mm without stiffener. So 22 mm is the safe thickness for this pressure condition, right? So this is part 1. Now, as far as part 2 is concerned, we will calculate the thickness of the shell when stiffeners are considered at 1 meter location. Stiffeners are placed at 1 meter interval. Okay, in that case L effective would be 1 now, not that 10 plus something, some 1 by 3 into hi plus sf, whatever we have done previously. So here 1 meter is the effective length. Okay, so L prime is considered as 1 meter, do by L as 5.2, and if you see this do by L prime, it is only up to 5, that we can extrapolate, okay, to find this k and n values. Okay, so that you can do, and once I'm having this k and m and modulus I know already, I can find out this plastic uh, the thickness corresponding to the plastic uh, failure. Okay, so here this is the design pressure. Just 1 minute please. So okay, now coming back to this, so considering this P as zero point 0.1 meganewton per meter square, and considering all other values, we can find T final as 7.67 and standard is 8. Okay, so again the same procedure for plastic failure, we will consider this thickness, because here do by L prime is 5.2, which is more than 5, so we will use this expression for plastic failure, right? And putting all values over here with this t, not this t, right? This t will be put over here. Okay, so it is coming as 0.295, which is greater than zero point 0.1, so we can have final thickness with stiffener as 8. This is the thickness of what? This is the thickness of shell with stiffeners, right? And if if it is coming lesser than this, sorry, if it is coming lesser than this, then what we need to do? We need to consider this pressure as design pressure, and we have to calculate thickness using this expression, not this expression. So once I calculate thickness using this expression, I will consider the next standard value available in table B1 as final thickness, and I do not need to go back and verify this, because once the thickness for plastic failure is in satisfied range, elastic failure will automatically be satisfied. Okay, now here you can focus, you can consider another point is that with a stiffener, thickness is coming as 8 mm. Without stiffener, thickness is coming as 22 mm, right? You can see here. So you can imagine the role of stiffener. It keeps the vessel so stiff that material in shell would be reduced. However, you put some material in stiffener, okay, stiffener material will also be counted, but the shell material will be reduced by significant value. Okay, so this is the role of the stiffener. Now we need to estimate the saving in shell material if a 18 centimeter channel is used as a stiffening ring. For these all parameters are known to me. I will calculate the uh, moment of inertia for the, what we can say, moment of inertia for structure. This is the moment of inertia for the structure, which is equal to this expression do square L Ts, okay, plus uh, As by L, okay, and F and 12E. And in this case, you need to keep in mind that this thickness of the shell is with the stiffeners. It doesn't mean that this t is multiplied over here, no. Okay, this is only the what we can say, the comment that t should be with stiffener, because we are calculating the moment of inertia, and in that case we already consider stiff that stiffeners are already placed. Okay, therefore this t shell should be with the stiffener, that is 8 mm, right? So in that case you can consider this as, and all parameters are given to me, so that is 1.056 times power minus 5. Okay, the condition to have the suitable stiffener is the moment of inertia of the structure should be lesser than moment of inertia of the ring. Okay, okay, of the stiffener. Okay, so if you compare this with this, of course this would be lesser than this, so you can imagine that 18 centimeter channel is a suitable stiffening ring for the vessel. Okay, now we need to estimate the saving in the shell material. So you can understand that without stiffeners, thickness is coming as 22, with stiffener thickness is coming as 8, but we need to consider some material in stiffeners also. So for that I need to find the number of stiffeners first. So number of the stiffeners means total length by spacing minus 1. Total length is 10 by 1 minus 1. So 9 stiffeners we need to place, we need to consider. We have to consider total weight of the ring, because weight of the ring, weight of the stiffener per unit length is given, so you need to find out the periphery. Okay, 9 is total number, pi do outer periphery, into weight per unit length, right? So total 2146.58 kg material we need to invest in the ring, in stiffening rings. So saving in the shell material is pi do, okay, outer diameter, into t without stiffener, that is 22, t with stiffener 8. So this is the saving, into tangent to tangent length into density. Okay, so this we need to consider as the material saved in shell. Okay, however we are investing in stiffener, so that I need to deduct. So total 15.8 ton of material will be saved when I am using the stiffener in this case. Okay, so in this way you can find out the you can find that significant saving is obtained, and with and without stiffener, how much difference in shell thickness we consider, we obtain, that we have seen with this example. Okay, I believe you are already you are getting all these points. Okay, and if you have any confusion you please discuss. And in the same line we have already seen whether channel is rigid enough to sustain the pressure or to avoid the vessel to collapse. Okay, so this is the condition. So this is all about external pressure vessel design. And we have already covered many topics like mechanics of the material we have discussed. We have discussed pressure vessel for shell head, and we have discussed compensation, we have discussed flange of the material. Okay, flange design, sorry, we have discussed flange design, we have discussed tall vessel design along with the support, and now this is external pressure design is design we have considered. So some I'm not having more topic, some small topics are left, 2 3 topics only, so that I will cover in next week, because Thursday and Sunday I'll not able to take class, as I'll be out of station. So next class will be on coming Tuesday. Okay, so please share the link for the same. So if you have any observation you please let me know, otherwise that's all from my side. Thank you.